In this video, we're going to be talking about valence bond theory and hybridized orbitals. So recall the orbitals that we already talked about, the s, p, d, and f orbitals. And now when you think about putting those orbitals together, those orbitals show us the electron density and where it is. And then how do those come into play when we're bonding? So Linus Pauling developed valence bond theory. He was searching for and expanding the understanding of electronic structure of atoms from the atomic orbitals that you'll recall from Chapter 7, and the electronic structure of molecules. And we needed a quantum mechanics-based model. So some assumptions are that a chemical bond between two atoms results from the overlap of the atom's atomic orbitals. The greater the overlap, the stronger and more stable the bond. So let's just take a look at hydrogen. Atomic orbitals, hybridized orbitals for bonding. So we're going to use the atomic orbitals to make hybridized orbitals. So a sigma bond, the first type of bond we'll look at, is a covalent bond. And remember, covalent means that we're sharing electrons, in which the highest electron density lies between the two atoms along the bond axis. So if you'll recall, hydrogen has a 1s electron. So it has that 1s orbital, which is spherical like this. Then we take another hydrogen with a 1s orbital. Then we smush them together, and you can see this area of overlap creates the bond. And here, this little letter here is called sigma. And that means that the electron density is right in between the two atoms. Later, we're going to look at an example where it's not right between them. So if the overlap is right between them, then this is called a sigma bond. So here we just took a 1s orbital, overlapped it with another 1s orbital, and that region there indicates the bond. Now, sometimes we're going to need to hybridize orbitals. So in that case, we just use the 1s orbitals that were already there. But here, we're going to show you how to use s orbitals and p orbitals to make what are called sp3 orbitals. Hybridization is the mixing of atomic orbitals to generate new sets of orbitals that form covalent bonds with other atoms. So if you recall your orbital diagrams and look at carbon here, carbon is 2s2, 2p2. So you have this s orbital and these three p orbitals. Now if we're going to bond them, as we know from, say, methane, for example, which forms a tetrahedral shape, you can't really use these s orbitals and these p orbitals to get it to bond uniformly and equidistant around the atom. So what we do is we kind of take these s orbitals and these p orbitals, shake them up together, and create four new orbitals that are degenerate, meaning equivalent in energy. So here you'll see the two p's are higher in energy than the two s's. But if we take the 1s and the three p orbitals here and mix them up together, and then we get four sp3 orbitals. So we took an s and three p's to make an sp3 orbital. So this is unhybridized. Say this is carbon right here. So those are the s and the p orbitals. But then if we hybridize them, now you can see that carbon has these different sp3 orbitals, which are located tetrahedrally around here, so that we can bond the hydrogens. So now you take those four hydrogens, which each have an electron in a 1s orbital, and then you're going to attach them to each of these sp3 orbitals to make a tetrahedral shape. And you can see that where that overlap is right there, that's your bonding. And in this case, it's right between the carbon and the hydrogen, so this is still a sigma bond. So these are our tetrahedral sigma bonds. So we're still looking at methane here. The sp3 hybridized orbitals are formed by mixing 1s and 3p atomic orbitals. Tetrahedral orientation of sp3 hybridized orbitals equals tetrahedral molecular geometry. So these are your hydrogens again, which each of them has a 1s orbital. And then the carbon here has 4 sp3 orbitals for them to attach to. And then we have sigma bonding right here between the carbon and each hydrogen. Here are some other examples of when we would see sp3 hybridization. So for nitrogen, bonding with 3 hydrogens, this is ammonia. And we've drawn Lewis structures of all of these in the previous videos, so if you want to look back at those, or the VSEPR theory, then you'll be able to see these. So again, nitrogen is 2s2, 2p3. So we're going to take that s orbital and all 3 of the p orbitals, and we're going to make 4 sp3 orbitals. Then we're going to take the 1s from each of these 3 hydrogens and stick them on there. Now, if you'll recall from the Lewis structure, NH3 has that one lone pair. So that lone pair is going to go into one of the sp3 orbitals. So 3 of the sp3 orbitals are going to bond with hydrogen, and then one of them is going to hold the lone pair. And again, this has that tetrahedral electronic geometry, but since one of them is a lone pair, then the overall shape is trigonal pyramidal. Then we can look down here. This is water, which we've also drawn Lewis structures of and looked at the VSEPR theory. Oxygen is 2s2, 2p4. And it has those 6 valence electrons. So again, we're going to mix up the s and the 3p to make 4 sp3 hybridized orbitals. Then for 2 hydrogens, each of them having a 1s orbital. So then you can see, remember with water, we have 2 lone pairs. So 2 of those sp3 orbitals are holding the lone pairs, and then 2 of them are sigma bonding with the hydrogen. So again, we have that tetrahedral electronic geometry, and for water, overall bent shape. Okay. And again, hybridization is one of these things that just requires a lot of practice, and it's kind of like learning a new language. So we can have types of hybridization other than sp3. So we just saw if you have sp3, that means you have the tetrahedral electronic shape. So now we're going to take a look at sp2 hybridization, which is going to be a trigonal planar shape. So here, we're going to take, this is our unhybridized carbon, and we're going to take, instead of taking all 3 of the p orbitals, we're going to leave one of those p orbitals alone, and we're just going to take 1s and 2 of the p orbitals to make 3 sp2. So I like to just count it here. S counts as 1, and then plus 2 is 3. So that means you have 3 total orbitals. And then we still have one unhybridized p orbital left over. So we took 3 of these here, and we left one of the p orbitals. So now we have 3 sp2 hybrid orbitals and 1 p orbital. We can do the same thing with oxygen. So oxygen, we could take the 2s and 2 of the p to make 3 sp2 orbitals. And then we can keep one of those p orbitals. And those unhybridized p orbitals are going to be left over because they're going to do something special. They're going to form double bonds. So let's take another look, a closer look at this sp2 hybridization and how we get pi bonding or double bonding. So a pi bond is a covalent bond in which electron density is greatest around, not along, the bonding axis. So in this case, we're going to take a look at bonding carbon and oxygen together. You can see formaldehyde down here. So there's a double bond right here. So what's going to happen, here's the carbon that we just looked at, and we have our 3 sp2 hybridized orbitals, and then this is 1 p orbital that we have left over. This entire thing is 1 p orbital. Then we did the same thing with the oxygen. We have 3 sp2, and this one p orbital left over. So if you look here, these two sp2s that are facing each other, we're going to smush those together, and they are going to form this sigma bond that's right between the carbon and the oxygen. Then these p orbitals, imagine you smush this together, then this p orbital is getting close to this one. So then where these overlap, they're going to overlap at the top and at the bottom. And so that makes this funny shape here and here. So that balloon on the top and the balloon on the bottom together make one pi bond. So that's your double bond. And you can see this is going to make it all come closer together. It's going to be a stronger bond, a shorter bond, and it's going to make it rigid. So if you just had the sigma bond, it would still be able to rotate, but this pi bond forces it to stay rigidly together. So again, sigma bonding is that bonding that's right there in between the two atoms, and then the pi bonding is on the outside of the bonding axis, not right in the middle, and that's your double bond. All right, so now we can also have sp hybridization. So that means we're just going to take one s, one p, and then we're going to leave two p's out. So then we're going to be able to form a triple bond with one sigma and two pi bonds. So now we're going to make this down here where you have hydrogen bonded to carbon, which is then triple bonded to carbon, and then a single bond to hydrogen on the other side. So right here we have carbon that's sp hybridized, which means you took one of the s's and one of the p's and you made these two. And then there's this one p bond that goes up and down, and then the p that goes in and out. So those are your atomic orbitals left over. Do the same thing with this one. So this 1s hydrogen is going to smush onto this sp and form a sigma bond right over here. This other hydrogen is going to smush onto the sp here, and that's going to form a sigma bond right between the carbon and hydrogen over here. Then the up-down p is going to overlap on the top and the bottom to make the second bond. And then the p coming in and out of the plane is going to overlap in the front and the back to make that triple bond. So you can see these balloons here. The balloon on the top and the bottom makes up one pi bond, and then the one in the front and the back makes up a second pi bond. So altogether, all this balloon animal nonsense in the middle here is a single sigma bond and then two pi bonds for a total of 3 bonds. So that's how you make that triple bond. And again, as we discussed already, that's going to be an even shorter bond because it's going to, all that electron overlap is going to pull those carbons closer together. And it's going to be very stiff, so you can't rotate around that bond at all. So that's our sp hybridization. And anytime you have sp hybridization, your molecule is linear. The next shape we're going to take a look at is trigonal bipyramidal, or the sp3d hybridization. So in the other ones, we were just using s and p orbitals to hybridize, and now we're going to take the s orbitals, the 3p orbitals, and then we're going to take one of the d orbitals to make sp3d. So if you count 1s plus 3 p's, that's 4, plus 1d is 5. So you have 5 sp3d orbitals. So that's what you would use for steric number 5, which is what we have over here. And these are all sigma bonds because they're happening right between the elements that we're interested in. So sp3d hybridization corresponds to trigonal bipyramidal. Then if we take another d orbital, so now we have 1s, 3 of these p orbitals, and then we're going to take 2 d orbitals. So you still have 3 d orbitals left over. And now we have 1, 2, 3, 4, 5, 6 sp3d2 orbitals. And this is our octahedral shape because our steric number is 6. So we mixed 1s, 2d, and 3p orbitals to make 6 sigma bonds. So again, this is that sigma bonding rather than pi bonding because it's right along the axis. All right, and this you can find in your textbook or on your handout, hybrid orbitals based on steric number. So as long as you can come up with that valid Lewis structure and then use your VSEPR theory to figure out a steric number, then you'll be able to figure out the hybridization. So if the steric number is 2, you have SP. So SP means one S and one P, so that's 2. Steric number 3, SP2. So if you have S, that's 1, plus 2 P's is 3, 3. So that's SP2. And so on. SP3, steric number 4, 5, 6. So as long as you can figure out that steric number, then you can figure out the hybridization. All right, so let's do a little bit of practicing. What are the hybridizations of the central atoms of the molecules SF4 and CO2? So let's go through these. And when we are looking for the hybridization, we are looking at that central atom. So the first thing you need to do are draw some Lewis structures. So here we have already drawn the Lewis structures. Here's SF4 and here's CO2. Then you're going to count the steric number around them. So from the steric number of the central atoms and the valence bond theory, we can determine the hybridization around the central atom based on electron pair geometry. So for SF4, it's steric number 5 because we have 1, 2, 3, 4, 5. So 4 bonding, 1 lone pair. And Sn equals 2 for carbon dioxide. So this double bond, remember, counts as 1 electron group, and this one counts as 1. So that's steric number 2. So then let's take a look at the SF4. The electron pair geometry associated with steric number 5 is trigonal bipyramidal. The lone pair means that the molecular geometry is seesaw. But that doesn't really affect the hybridization. So the steric number 5 is what's really important here. The S atom has an expanded octet of 10 valence electrons, which means sp3d hybridization. So remember, this is 1 plus 3 is 4 plus 1 more is 5. All right, so steric number of 5 corresponds to sp3d. For carbon dioxide, the electron pair geometry associated with steric number 2 is linear. And the 2 double bonds mean that there are 2 unhybridized p orbitals. So remember, for that double bond, you have that pi bonding for those unhybridized p orbitals. The carbon atom has sp hybridization. So steric number 2 is sp. So why is shape important? Molecular recognition. So the process by which molecules interact with other molecules in living tissues to produce a biological effect. So one example of this is ethylene. This is what ethylene looks like, and this is a ripening agent. So it's given off naturally by bananas, and that makes them ripen. So this molecule interacts, it bonds to something because it's the right shape, like a lock and key, and that makes ripening happen. So if they pick the bananas where they're not ripe, and then you want to artificially ripen them, you can kind of gas them with ethylene, which is basically exactly what would be happening in nature. But then you can ship them, and ripen them later. All right, so all of these atoms are in the exact same plane. All right, so this, I'm not going to expect you to produce a lot of drawings, but I do want you to be familiar with drawing larger molecules and the different ways that they can be represented. So if you look at this column, these are all the exact same compound represented different ways. This column, these are all the exact same compound, just represented different ways. So this top one, these are Lewis structures, which we've already looked at and you know how to draw. Then you have these Kekulé structures, which is essentially a Lewis structure, but without the lone pairs drawn on. So you might see some drawings later that you have to answer questions about, and you're going to have to figure out that those lone pairs belong there. So if you saw this oxygen, you would know, you see these 2 bonding ones, so that's 4 electrons, but you know it has to be following the octet rule, so then you know there have to be 4 more electrons around it. So you're going to kind of have to reason through it to make sure you figure out where those lone pairs would be, even if they're not drawn. Then we have these, which are called condensed structures. So you'll see this CH3 corresponds to a CH3 group like this, where you have the carbon and 3 hydrogens attached. Then in the middle of carbon chains, you can see you have these CH2 groups. So CH2, 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 and then at the end, another CH3. So when you see these, I want you to know that it should look something like this. Then we have these carbon skeleton structures. So these are kind of the most minimalistic and what you would see a lot of if you're taking an organic chemistry class and the professor's trying to draw really quickly. So at every point, that means there's a carbon atom. So right here, right here, right here, right here, and right here. So this is 5 carbon atoms, just like you see in the Lewis structure. And they're going to be saturated with hydrogen. So since it's a single line, that means it's all single bonded. So then you just put hydrogens around so that each carbon has 4 bonds. All right, and then this one, you can see it's kind of the same deal. So here's a carbon, 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 but we draw in the oxygen and the double bond. And then you just know that each one of these has to have 4 bonds on it. So you fill in hydrogens where you need to. So I mostly just want you to know that these large molecules can be drawn in many different ways. And to be able to kind of recognize some of these and figure out where lone pairs belong if they're not drawn in. I don't expect you to be able to produce drawings like these ones down here. Okay, so let's just do a quick practice so we can kind of feel familiar. So we're going to draw a Lewis structure, condensed formula, and carbon skeleton structure for a straight chain octane, which is a chain of 8 carbons surrounded by or saturated with hydrogen atoms. So maybe pause it and see if you can do that. All right, so the Lewis structure, you just take 8 carbons, and then you're going to put hydrogens all around it, so each one has 4 bonds. So again, it's always going to start with a CH3, end with a CH3, and every piece in between is a CH2. So then for the condensed formula, you have your CH3 on both ends, and you have 6 CH2 groups because there are 6 of these here. 1, 2, 3, 4, 5, 6. And the carbon skeleton structure, remember, each of these counts as 1 carbon, and it's implied that it's saturated with hydrogens otherwise. Okay, so now we're going to kind of put that all together, being able to look at a bigger compound, take what you know about VSEPR theory, and then identify hybridization. So for example, I have it all drawn out here for you, but let's say you saw this molecule. I would want you to be able to go through each of these and say what the hybridization around each one of these is. So when you do that, you look at this first carbon, and then you kind of ignore the rest of the molecule, and you just say, okay, carbon has a steric number here of 1, 2, 3, 4. So that's sp3. Let's go to the next carbon. 1, 2, 3, 4. Steric number 4, also sp3. This oxygen here, 1, 2, 3, 4. So that's also sp3 hybridization. Even though these are tetrahedral shape and this one's bent, the electronic structure is tetrahedral. Then if we look at this one, 1, 2, 3, 4, also sp3 hybridization of this carbon. Then let's go to the next carbon, find the steric number, 1, 2, 3. So steric number 3 corresponds to trigonoplanar and sp2 hybridization. Then we'll look at this last carbon, and we see the steric number is 1, 2, 3, also sp2. So I'll want you to be able to go through these bigger molecules and for each one of these say what the hybridization and the shape is around that. So let's do a practice together, and then you're going to practice a couple on your own. All right, so we basically just want to go through each one of these and say what it is. So also I want you to take a look at these oxygens and see that they don't have the lone pairs specifically drawn on there, but they are implied. So this oxygen has 2 bonds, so that's 4 electrons. So it must have 4 more electrons, which are lone pairs here. So the steric number there is 4. Same one here. This oxygen also has 2 bonds, so that's 4 electrons, so it must have 2 lone pairs that are not shown. So let's go through all these and see what they are. Remember this CH3 group? That means that the carbon is bonded to an oxygen and 3 hydrogens, so a steric number of 4. All right, so let's take a look. We want to identify the hybridization for all of these. So we're not going to look at hybridization for these external atoms, but just the central ones along the chain. So let's find the ones that are steric number 4, which corresponds to sp3 hybridization. So this one, as we said, even though you only see these 2 bonding groups, there are also 2 lone pairs on here, which are just not shown. This one also, there are 2 lone pairs there that are not shown. This one is bonded to 4 things, so sp3 hybridization, tetrahedral shape. Then it looks like all the rest of them are steric number 3, which is sp2. So if you take a look at any of these, you look at this carbon, it has 1, 2, 3 groups around it. Steric number 3 is sp2. This one, 1, 2, 3. This one, 1, 2, 3. 1, 2, 3. So you can see all of these have 1, 2, 3. All right, even this guy, 1, 2, 3. So the shape around all of those is trigonal planar. These ones over here have an electronic shape of tetrahedral. And these areas with the oxygens, since 2 of those are lone pairs, it's tetrahedral electronic shape and bent overall geometry. So I want you to practice these ones on your own. So determine electronic shape, molecular shape, and hybridization about each central atom. So I'll just show you. So central atom means this one, this one, this one. And then for this guy over here, it's this carbon, and this carbon. So pause the video now and see if you can answer these. It's important to try to work problems out by yourself rather than just watching the answer. Okay, so let's go over these problems here. So the carbon here has 1, 2, 3, 4. So that corresponds to sp3. This one has 1, 2, 3, which corresponds to sp2. This one, you can see the lone pairs are not drawn there, but there are 2 lone pairs. So that's steric number 4, which corresponds to sp3. Then let's look over to this one. So this one has 1, 2, 3, 4, steric number 4. So the shape around that is tetrahedral. This one has 1, 2, so steric number 2, the shape is linear, and the hybridization is sp. This one, steric number is 1, 2, shape is linear, hybridization is sp. All right, so this one was tetrahedral, this one was trigonal planar, this one had electronic shape of tetrahedral, but overall shape of bent. All right, so just make sure you practice these more: Lewis structure, VSEPR theory, hybridization of orbitals.